The next speaker is Dr. Vaibhav H Wasnik from IIT Goa. He will be talking about revisiting multiple thermal reservoirs, stochastic thermodynamics.
Okay, so I'll be talking on this topic of multiple thermal reservoirs, stochastic thermodynamics. So this is, the work that is there on this archive paper. So let me just get to it. Most of the work that is there in this topic has been on Markovian systems. So basically, these are described by master equations. And there what you have is, this thing is a transition rate. This is the probability that the system is in a particular energy, system is basically having a particular energy value. And in case the system is connected to a thermal reservoir, which is a single thermal reservoir, you have this detailed balance condition. The main thing is when the system is connected to two thermal reservoirs, okay, there is this result that is there in the literature that the transition rate that is there is equal to the transition rate, assuming the system was just connected to one thermal reservoir, which is corresponding to temperature T1, or plus the transition rate, assuming the system was just connected to the thermal reservoir T2, okay? And obviously these things obey the detailed balance equations. What we attempt to show, just we make an argument to show that this thing is not, there are some issues in this relationship. And then after we go to show that the generic evolution that is there of these kind of systems is non-Markovian. Just a very simple argument to the first point. You're having the system connected to two thermal reservoirs, one is at T1, one is at T2. These are analytical functions of the temperature. They're only dependent upon these energies, epsilon I, epsilon j. Since the analytic, we can basically consider the limit T1 is equal to T2 is equal to T. In that particular case, what you get is the system by itself, the T1, T2, all you have is that the system is connected to a single thermal reservoir of temperature T. So what you're having is this thing is basically the transition rate for thermal reservoir temperature T, whereas these 1 and 2, these temperatures also temperature T, that's why these have to be equal. And you can see that at least at this limit, this equation is not getting satisfied. Now this thing is just considering this particular regime where, I took that particular limit and I showed that this thing is not true. There is a mathematical argument which is not relying on this T1 equal to T2 limit. It is more mathematical, it can be found in this paper. The second part that is there, I would like to show that, this is the second part where I'll show that the evolution that is there of these kind of systems is going to be non-Markovian. So if you're having two thermal reservoirs, at the minimum what you will have is at least there are 2 points in space where this particular reservoirs will attach, okay, to the particular system. Now I take the simplest possible case I can find. I'm having these 2 points. You can basically interact energies between there can be an exchange of energies between these 2 points. I'm saying each of these 2 points can have these energies, and I'm considering the whole system, this whole thing as the system, okay? So this is my just sample, which I'm basically going to try to understand. And I'm going to show that this composite evolution is non-Markovian. The way to see that is, first thing to note is that in a time interval dt, the exchange that is there is just going to be happening with only one of these points. Exchange of energies with the environment is going to happen only at one of these points, because if you're going to have simultaneous exchange at 2 points, the probability of that is going to go as dt squared and is going to be minimal compared to the dt. Okay. So now in case I'm looking at a particular transition where I'm having the total system energy, which was 3 epsilon, it goes to 5 epsilon. In case this is Markovian, I should basically have that it should go as the probability of the entire system having energy 3 epsilon times this transition rate times dt. The main thing is, if I look at this probability of it having an energy 3 epsilon, it can be written in this kind of a format where either one has energy 2 epsilon, 2 has energy epsilon, and vice versa, or one has epsilon, energy 3 epsilon, 2 has energy 0, and vice versa. The transition rate that is there is going to be when either, this one is going to get an energy of 2 epsilon to become, or at this 2 that is there is going to get an energy of 2 epsilon. In order for this particular process, where one gets an energy of 2 epsilon, what you have is it has to basically get to an energy of 4 epsilon, or the system 2 is getting an energy of 2 epsilon, it basically moves to an energy of 3 epsilon. So this is the entire contribution over here. And you're going to be having similar contributions like this for the rest of the transitions. Now the thing is, when you're considering the other reverse transition, where you're going from a system having a total energy of 5 epsilon to 3 epsilon, what you have is obviously, first of all, the systems that are there, the various energies that the system of energy 5 epsilon that is there, the various ways in which you would have this energy distributions is, one is having energy 2 epsilon, 2 is having energy 3 epsilon, and vice versa. One is having 5 epsilon, 2 is having 0, and vice versa. One is having 4 epsilon, 2 is having epsilon, and vice versa. The main thing is, as far as over here, what you will have is one of these, 1 or 2 is basically going to lose an energy of 2 epsilon. So over here, you can basically lose an energy of 2 epsilon. There is no problem. But when you're looking over here, that is over here, you can only have one. System 1 can basically lose an energy of 2 epsilon. 2 cannot lose an energy of 2 epsilon because that is not allowed. Okay. So that transition rate is only going to be where you're going to have this 4 epsilon jumping, 4 epsilon going to 2 epsilon, okay, for the system 1. So that is the only difference that is there from the previous case. Now what we do is, we consider the limit, T1 is equal to T2 is equal to T. This thing is, the equation that we wrote previously had to be true for any temperatures. We consider the limit where the temperatures are equal. What you'll have is that these transition rates are equal. What we are calling 1 and 2, they are going to be equal. Also the probabilities that we have, because the probabilities are only functions of temperature and the time at which you're considering, these probabilities will also be equal. Now let us get back to our original equations. Okay, so the first equation that we had was when you're going for the entire system. Okay, so these are the two, let me look, okay, come here, yeah. So if I'm looking at this transition from 3 to 5, these are the equations that we are going to be having, okay. And now in order for this thing to be Markovian, what we should have is that all of these should be able to be grouped together into this, okay. For that to happen, you should be having that these terms are equal to each other, okay. For all values of, these terms have to be equal to each other. And if you're going to say that these terms are equal to each other for a generic value of epsilon, the condition that you get is that this omega w epsilon prime is basically a function of the difference between the two. Okay, if you just substitute that here, you see that it can be written in this kind of a form. The second case is, we had this other problem where we are basically going from a high energy to a low energy. And as I had said that there will be this issue that, you will only have one of these jumps from 4e to 2e, okay. Now in this particular case, in case we want to group all of these probability terms in this kind of a format, okay, the solution that we'll have for any particular generic value of epsilon is that these differences that are there, okay, this thing that is there is basically just given by f of the difference between the two. But when we are coming over here, we should have this thing as twice of f of the difference of the energy levels, okay. Only in that particular case, this grouping is possible. So now moving forward, now what I do next is, I basically, this is the formula that I had, okay. I basically turn on the temperatures, I change the temperatures now, T1 and T, I basically switch the temperatures to the T1 and T2, they're different. In that particular case, what I basically see is, I just make the substitutions of what I had before. So this was basically just dependent upon F. So it will basically now depend upon the temperature, F times 2 epsilon. That is what I have here, F1 times 2 epsilon plus F2 times 2 epsilon. Everything fits in together properly. Okay, over here, everything basically fits in together properly. Whereas in the second case, what I have is, because I had this constraint, okay, that these things would basically be different. Sorry, because I'm out of time. What I have is that when I make the substitution, I'm having extra factor of 2 over here, okay. And when I basically try to put these two together, okay, try to see whether I can get this thing in some kind of a form where I'm just having one of P, P of 5 epsilon, I cannot do it because I'm getting some other terms over here, okay. And because of that, the evolution that I see is basically turning out to be, not Markovian. So what I've shown is that the evolution of this generic system connect to multiple reservoirs is non-Markovian, and what we need is additional research to understand things such as fluctuation relations for these systems.
Time for questions.
I was not sure how you are defining the system, because multiple 2 or 3, if you are using enough coordinates to describe enough degrees of freedom to describe the system, and if your dynamics, it depends on whether you are defining the dynamics as a Markovian or not, then whole system should be Markovian in those full degrees of freedom space. Now, of course, if you take a reduced degrees of freedom, that system will not be Markovian.
No, so here what I'm basically doing is, I'm saying when I considered this entire system to begin with, I just considered the system as 2 points, okay?
But what are the degrees of freedom for a system?
No, right now all I'm saying is that they're just 2 points, and these 2 points, they can basically have these energies. Okay, each of these can basically take on these energies.
But there's a joint distribution, right? The distribution of this did not factorize, right? Like in your equation you wrote, I think P1 of epsilon, P2 of 2 epsilon. The distribution need not, what are these P1 of epsilon?
No, so this thing is a probability that the one is basically having an energy level, it's basically an energy of 2e.
But why should that factorize?
What do you mean, why should we factorize?
It's a joint probability of one having 2 epsilon and other having epsilon, right? That need not be factorized of these 2 probabilities, no?
No. What I'm saying is okay, in case I'm basically having the entire system is having an energy of 3 epsilon, okay? So if I'm having the entire system to have an energy of 3 epsilon, okay, this is the probability distribution, I'll basically be factorizing it. But now if I'm,
what I'm saying is that to describe if I have an n particle system, I cannot just describe the whole system just based on the energy of the system, right? That doesn't have enough variable to describe the system.
No, over here what I'm saying is, let us consider the whole system. The whole system has basically a total energy, one total energy, okay? Now in case I'm basically realizing this total energy, for example, if the total energy of the system, wait a sec, is 3 epsilon, okay? In order to get this 3 epsilon, okay, how would I get 3 epsilon? Either one of them is epsilon, another is 2 epsilon, or another one of 2 epsilon, right?
So there are two things. One is, of course, this even that right-hand side need not factorize. Okay, it should be P of 2 epsilon, comma epsilon. Right? Because I have to have enough degrees of freedom to describe the system. Because like if I want to describe the gas in this room, I cannot just describe by just the energy of the gas, right? I mean, that will of course not be Markovian, but if I need all the degrees of freedom of all the particles to describe.
Yeah, but over here, all I'm saying is that I'm just having the only degree of, okay, might be I'm getting confused with this word degree of freedom over here. All I'm saying is, I'm just considering I'm just saying that, okay, let me consider a system having a total energy, okay, and this total system that is just made of 2 objects, okay, each of them can only have these number of energies. That is all that is there to the problem.
Yes.
Yeah. Now you're saying that, okay, there should be some extra degree of freedom inside the problem. Is that what you're saying?
I mean, even that problem should be described by the joint distribution, not a product of the two energies.
No, but in case I'm say having like,
I mean, I don't understand why you are writing P1 of 2 epsilon times P2 of epsilon, for example. I mean, why should it be a product of the two probabilities?
yeah, we can just do that. Yeah, okay.
Okay, so let us thank the speaker.